There is a period in the history of the universe that has no name in any human language because nothing alive existed to witness it. No stars, no galaxies, no light of any kind. Only hydrogen, cooling, falling, waiting. And for somewhere between 100 and 400 million years, the entire cosmos was dark. Not metaphorically dark. Physically, totally, impenetrably dark. And yet, something was already growing in it. Something that should not have been there. Something that, when we finally saw it, stopped astronomers mid-sentence and forced them to ask whether everything we believed about the origin of the universe was not incomplete, but categorically wrong. The universe had a childhood we never expected to be complicated. Then we built a telescope powerful enough to see it. And nothing has been the same since. To understand what has been found, you need to understand what was there first. Or rather, what wasn't. The story of the universe's first light, its very first chapter, is one of the most disorienting things that physics has ever produced. Disorienting because it describes a cosmos that is simultaneously on fire and completely blind. A universe that is screaming with energy and yet producing not a single photon that can travel more than a few centimeters before being absorbed. Picture it, the universe at 1 second old. The temperature sits at roughly 10 billion degrees Celsius. Every point in space is filled with a plasma so dense and so hot that light cannot move. Photons are born and immediately reabsorbed. Born again and reabsorbed again. This isn't darkness, it's something stranger. It is a universe drowning in its own radiation, unable to let any of it escape. This early epoch lasted for approximately 380,000 years. That sounds like a long time until you remember that the universe is currently 13.8 billion years old. It spent its first 0.003% of its existence locked inside a glowing, opaque fog of its own making. And then, at the 380, 0-year mark, something happened. Cosmologists call it recombination, a word that has always struck me as unnecessarily dry for one of the most significant physical events in the history of existence. The universe had expanded enough, cooled enough, that free electrons could finally join protons and form stable neutral hydrogen atoms. In doing so, they removed the medium through which photons had been scattering. The universe became transparent. For the first and only time in history, light could travel freely across the cosmos. That light, stretched by 13.8 billion years of cosmic expansion, until it glows as cold microwave radiation, is what we detect today as the cosmic microwave background, the afterglow of the Big Bang itself, imprinted on the sky at a temperature of just 2.725 degrees above absolute zero. It is, in a very real sense, the oldest photograph that can ever be taken. And when we look at it, we see a universe that is almost perfectly smooth, almost perfectly uniform. Temperature fluctuations of no more than 1 part in 100,000, a universe that, at 380,000 years of age, contained the seeds of everything, but had not yet grown any of it. Then the lights went out. This is the moment that cosmologists call the beginning of the cosmic dark ages. The universe had become transparent, yes, but transparent to what? There were no stars yet. There were no galaxies. There were no black holes accreting material and radiating X-rays. There was neutral hydrogen, slowly cooling, slowly clumping under the gravitational influence of dark matter halos that had been growing since the Big Bang. There were regions of gas that were incrementally denser than others. Those 1 in 100,000 fluctuations in the microwave background marking the eventual seeds of structure. But nothing was yet lit. The universe, for what astronomers estimate to be somewhere between 100 and perhaps 400 million years, was completely, utterly dark. A darkness not merely of the absence of stars, but of the absence of any radiating object of any kind. We cannot observe this era directly. Not because our telescopes aren't powerful enough, though they weren't, until recently, but because neutral hydrogen absorbs ultraviolet light so completely that observations through it are impossible. The cosmic dark ages are, by their very nature, a sealed room, a chapter of history written in a language we have no instrument to read. The only way we might glimpse their end is to find the first objects that broke through them. the first galaxies or stars that began generating enough ultraviolet radiation to ionize the surrounding hydrogen and punch a bubble of transparency through the fog. That process, the gradual reionization of the universe's hydrogen gas, is called the epoch of reionization, and it represents one of the last great observational frontiers of modern cosmology. For decades, that frontier was theoretical. Elegant models, supercomputer simulations, educated extrapolations from what we could observe at lower redshifts, but no direct glimpse of the objects that did it, no census of the actual galaxies that lit the cosmos up, no measurement of when exactly the darkness ended and the first permanent light began. That changed. With a mirror 6.5 meters wide, kept colder than the outer edges of the solar system, orbiting at the second Lagrange point 1.5 million kilometers from Earth. It changed when the James Webb Space Telescope opened its golden eye and really looked, at the edge of time. And what it found there was not what anyone predicted, which raises three questions that will thread through everything that follows. How did a galaxy the size of a moderately small irregular, 1/600 light-years across, become so bright, so massive, and so chemically enriched in less than 300 million years? How did another galaxy, sitting deep inside the opaque fog of the Dark Ages, manage to broadcast a signal that should have been absorbed before it travelled more than a few kiloparsecs? And what does the sheer abundance of these objects tell us about a universe whose formation we thought we understood? The answers are stranger than the questions, and the questions are already extraordinary enough. To appreciate why these recent discoveries matter, you need to spend some time with the physics of neutral hydrogen, not because it is technically demanding, it isn't, but because once you understand what neutral hydrogen does to light, the discoveries of the last 2 years become not merely remarkable, but genuinely vertiginous. Neutral hydrogen is, by mass, the most abundant element in the universe. It constitutes roughly 75% of all ordinary baryonic matter. In the epoch immediately following recombination, from about 380 zeros and years after the Big Bang through to at least 100 million years, and possibly much longer, the universe was saturated in it. Not in the loose, diffuse sense that gas permeates the modern interstellar medium. The intergalactic medium of the cosmic dark ages was genuinely dense with neutral hydrogen, filling the space between whatever protostructures were slowly forming. A fog that was, from the perspective of ultraviolet photons, essentially impenetrable. This is not metaphor. The Lyman alpha transition, the specific wavelength of ultraviolet light produced when a hydrogen electron drops from its first excited state back to its ground state, has a cross-section for absorption by neutral hydrogen that makes it one of the most heavily attenuated signals in all of astrophysics. A photon at the Lyman alpha wavelength of 121.6 nanometers that tries to travel through a universe still composed mostly of neutral hydrogen has a mean free path measured in kiloparsecs at best. In a universe that spans billions of parsecs, that means it goes almost nowhere. The intergalactic medium of the Dark Ages is, for Lyman alpha photons, a wall. This is the Gunn-Peterson trough, named after the two physicists James Gunn and Bruce Peterson, who predicted in 1965 that spectra of any object seen through a sufficiently neutral intergalactic medium would show a complete blackout at wavelengths shorter than Lyman alpha. Astronomers observe quasars at redshifts above about 6.5. They see exactly this, a catastrophic drop in flux at the blue side of the redshifted Lyman alpha wavelength. The signal doesn't just diminish, it disappears, the spectrum goes flat. It is as though someone has drawn a black curtain across the entire universe at that point in time. The Gunn-Peterson trough gave us our first empirical handle on when reionization ended. The fact that high redshift quasars showed it confirmed that the universe at redshifts greater than roughly 6, corresponding to a cosmic age of about 1 billion years, was still substantially neutral. Below that redshift, the trough lifts. The universe becomes increasingly transparent. Reionization completed somewhere in that window, between about 500 million and 1 billion years after the Big Bang. At the beginning of reionization, the moment when the first ionizing sources lit their immediate surroundings and began carving the first bubbles of transparency, that was still hidden from us. To see the beginning of reionization, you need to observe at higher redshifts. You need to look back past redshift 10, past redshift 12, past redshift 13, into a universe where perhaps 90% or 95% or even 99% of the hydrogen between galaxies is neutral. And to detect anything at those distances, you need a telescope that can collect infrared light, because the expansion of the universe has stretched the ultraviolet light from those early galaxies so far into the infrared that no ground-based observatory and no previous space telescope could see it with sufficient sensitivity. The Hubble Space Telescope, for all its extraordinary legacy, had a mirror just 2.4 meters across. It could not collect enough photons from objects at redshifts above about 12 to do meaningful spectroscopy. It found candidates, tantalizing hints of objects that photometric analysis suggested might be extraordinarily distant, but it could not confirm them with the precision that science demands. Without a spectrum, without a measured redshift, a candidate is not a discovery. It is a rumour. For years, rumours were all we had. There were photometric candidates at redshifts that, if confirmed, would have shattered every expectation about how quickly the early universe assembled its first structures. Objects that, according to their apparent brightness and colour, seem to require redshifts of 12, 13 or even higher. But photometry can be fooled. A dusty galaxy at moderate redshift can masquerade as an extremely distant galaxy at high redshift, without the definitive fingerprint of a spectroscopic redshift, without measuring the precise wavelength of a known emission or absorption feature, and using it to calculate exactly how much the universe has expanded since that light was emitted. None of it could be trusted. This is the circumstance into which the James Webb Space Telescope was born. Its 5-meter primary mirror, assembled from 18 hexagonal gold-plated beryllium segments, collects more than 6 times the light-gathering area of Hubble. Its near-infrared spectrograph, built by the European Space Agency, can simultaneously obtain spectra for up to 100 objects at a time using tiny programmable shutters, each roughly the width of a human hair. Its operating temperature, kept at around -233 degrees Celsius using passive cooling and a 5-layer sunshield the size of a tennis court, suppresses its own thermal emission to levels that allow it to detect the faintest signals the cosmos can offer. Webb was not designed to photograph distant galaxies in the way that the iconic Hubble Deep Fields did. As glittering portraits of the universe's past, it was designed specifically and deliberately to answer questions about the first billion years of cosmic time, to pierce the fog of the Dark Ages, to find and characterize the sources responsible for reionization, to take for the first time a census of the universe as it was in its earliest infancy. Nobody fully anticipated what that census would find. The JWST program, the JWST Advanced Deep Extragalactic Survey, was one of the flagship programs to pursue these objectives. It combined the expertise of 2 of Webb's instrument teams, NearCam and NearSpec, in an ambitious campaign of deep imaging and spectroscopy targeting the Diok South Field, one of the most intensively studied patches of sky in modern astronomy. With a total allocation of hundreds of hours of observing time, JWST was designed to build a sample of hundreds of galaxy candidates at redshifts above 8, and to confirm as many as possible with spectroscopy. Its science team included some of the most experienced observational cosmologists in the field. Daniel Eisenstein of the Harvard Center for Astrophysics, who led the survey overall, Andrew Bunker from Oxford, Roberto Maiolino from Cambridge, Brant Robertson from UC Santa Cruz, Stefano Carniani from the Scuola Normale Superiore in Pisa, and Kevin Hainline from the Steward Observatory at the University of Arizona, who would be among the first to see what the program had found. In early 2023, that program returned an anomaly, an object, bright enough to catch attention, distant enough, if the photometry was to be believed, to be the most remote galaxy ever confirmed. but so bright and apparently so large that every instinct of experienced astronomers said it couldn't be real. And yet there it was, sitting in the JWST data at coordinates right ascension 3H 32 MEB 3689s, declination minus 27 degrees 46 49.33 seconds in the constellation of Fornax, waiting, daring the team to look again. But while the JWST team was wrestling with that anomaly, another question was rippling through the field. A question that was not just about one galaxy, or even 10, a question about all of them, because Webb, in its first months of operation, was not finding too few early galaxies. It was finding too many, far too bright, far too massive, and that was a problem of an entirely different order. In science, the most dangerous result is not a null result. It is not the experiment that finds nothing. The most dangerous result is the one that finds exactly what your model predicts, because it gives you the comfortable illusion that your understanding is complete. The genuinely productive result, the one that eventually rewrites textbooks, is the one that finds something impossible, something your model explicitly forbids. By the end of 2022, within months of the James Webb Space Telescope achieving full operations, the cosmology community was confronting exactly this kind of result. Webb's deep field imaging was producing candidate galaxies at redshifts of 10, 12, 13, objects apparently formed within the first 500 million years of cosmic history, that were not merely slightly brighter than models predicted. They were orders of magnitude brighter. They were so bright, and apparently so massive, that several physicists made public statements, cautious, qualified, but unmistakable in their direction, suggesting that standard cosmology was, at minimum, in need of revision. The standard model of cosmology, the lambda CDM framework, which stands for lambda cold dark matter, is one of the most precisely tested theories in all of science. It describes a universe composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, governed by the equations of general relativity and the physics of the very early universe that we know from the cosmic microwave background. It makes specific, quantitative predictions about how structure formed in the universe, how the first overdensities in the primordial density field grew under gravity, how dark matter halos assembled, how gas cooled inside those halos to form stars and eventually galaxies. The lambda CDM model predicts that galaxy formation is a gradual process, hierarchical in nature, as small structures form first and merge over time into larger ones. It predicts a luminosity function, a statistical description of how many galaxies of a given luminosity exist at a given cosmic epoch, that rises smoothly with time. The further back you look, the fewer bright galaxies you should find. They simply haven't had time to assemble. Webb disagreed. In the first year of observations, the number of bright galaxy candidates at redshifts above 10 exceeded theoretical predictions by factors of several. The UV luminosity function at these epochs was not a smooth, gradual rise. It had a bright end that was, by the standards of every model, anomalously overpopulated. There were galaxies at redshift 10, 11 and 12 that, based on their luminosity and inferred star formation rates, appeared to require stellar masses that the universe simply should not have been able to assemble in the available time. A set of 6 candidate galaxies, imaged in some of the first JWST deep field data and identified by a team led by Ivo Labbe of Swinburne University, appeared to have stellar masses of between 10 billion and 100 billion times the mass of the Sun. Masses that, if confirmed spectroscopically, would have required them to have assembled essentially all their stars in the first few hundred million years of cosmic history. The team was careful to note the uncertainties involved. Mass estimates from photometry alone carry significant error bars. Some candidates, when followed up with spectroscopy, turn out to be at lower redshifts than first suspected. Dusty interlopers, photometric imposters, some do not. Some turn out to be exactly what they appear to be. I want to be honest about the state of this problem as it stood in 2023. The community was not in a state of crisis, not the way a non-specialist might have interpreted some headlines. No single discovery in that first year definitively broke the lambda CDM model. What happened instead was something more subtle and, I would argue, more scientifically significant. The ensemble of early JWST results created a persistent, systematic tension with theoretical predictions that could not be fully explained by observational uncertainties or selection effects. The bright galaxy problem, as it became known, resisted every simple explanation that was offered. Several mechanisms were proposed: that early galaxies might form stars with greater efficiency than we had modelled, losing less gas through supernova feedback and retaining more material for star formation; that the initial mass function of early stars, the distribution of stellar masses produced per unit of gas, might be skewed toward heavier, more luminous objects; that active galactic nuclei might be contaminating some photometric samples, adding AGN luminosity to what appeared to be pure stellar emission; that dust properties in very early galaxies might differ from local ones in ways that affect mass estimates. Each of these explanations could account for some of the excess. None of them could account for all of it. The tension remained. And then, in January 2024, it deepened in a way that changed the conversation. In January 2024, the JWST team pointed Webb's near-infrared spectrograph at the anomalous source they had been tracking since early 2023. They scheduled 9 hours and 40 minutes of continuous observation. The spectrograph collected photons, the data were processed, and when the spectrum was finally produced and the team examined it, there was no ambiguity, no wiggle room. The source had a spectroscopic redshift of 1432, a redshift of 1432. In cosmological terms, this corresponds to a cosmic age of approximately 290 million years after the Big Bang. The light that the telescope captured had been travelling through the universe for 4 billion years before it arrived at the mirror of the Webb Space Telescope. The galaxy that produced it had not existed for the overwhelming majority of the universe's history. It was a relic of an era so early that the very concept of a galaxy, a gravitationally bound collection of stars, gas and dark matter, was barely beginning to be possible. The object was designated JWST 14-0, and it was immediately the most distant confirmed galaxy in the history of human astronomy. But its distance was almost the least remarkable thing about it, because what JWST 14-0 was, its size, its luminosity, its chemistry, was something that no model had predicted, and that the team, even after confirming it with 10 hours of spectroscopy, struggled to fully explain. At a redshift of 1432, JWST 14-0 is not a wisp. It is not the faint, tiny, barely resolved smudge that theory had suggested the first observable galaxies would be. It spans 1,600 light-years across, not a particularly large galaxy by modern standards, but for a galaxy that formed when the universe was less than 300 million years old, a size that implies it has already accumulated an extraordinary amount of baryonic matter. Its luminosity is such that it is producing somewhere between several and perhaps 20 times more ultraviolet light than models of this epoch predicted. It contains, based on the MIRI observations reported by team member Jake Helton, emission lines consistent with the presence of both hydrogen and oxygen, meaning that ionized gas of significant chemical complexity already exists within it. That last point deserves its own paragraph, because it is the one that stopped me most completely when I first encountered it. Oxygen is not a primordial element. It does not emerge from the Big Bang. The only oxygen that exists in the universe is oxygen that has been manufactured inside stars through nuclear fusion, and then expelled into the surrounding medium when those stars died, through winds, through supernovae, through the complex process of stellar evolution and death. For JWST 14-0 to contain detectable oxygen at a cosmic age of 290 million years, multiple generations of stars must have already completed their entire life cycles within it. They must have been born from essentially pristine hydrogen and helium gas, fused that gas into carbon, nitrogen, oxygen, and heavier elements in their cores, and then died, in some cases explosively, enriching the galaxy's interstellar medium with those products. All of this within a window of less than 290 million years. This is not impossible, but it requires a rate of star formation and stellar evolution so rapid, so intense, that it challenges every model of early galaxy formation that existed at the time of the discovery. As Stefano Carniani of the Scuola Normale Superiore in Pisa, one of the lead scientists on the JWST program, put it in the press release accompanying the ESO oxygen detection, the galaxy appeared to be an adolescent where only babies were expected. The observation is exact and the implication is sharp. The universe, at 290 million years, was not supposed to be capable of producing adolescents. And yet, there it was, measured, confirmed, real. But there was another object also found in the JWST data that presented a different and, in some ways, even more philosophically confounding problem. An object that was not merely more massive than expected. An object that was apparently doing something physically that the rules of the Dark Ages explicitly forbade. There is a rule in the physics of the cosmic Dark Ages that was until recently considered inviolable. It goes like this. Any galaxy that existed during the Dark Ages, during the epoch when the intergalactic medium was still predominantly neutral hydrogen, could not be observed through the Lyman alpha emission line. The neutral hydrogen would absorb it, every single Lyman alpha photon that the galaxy emitted. The brightest, most characteristic emission line of star-forming galaxies would be swallowed by the surrounding fog before it could escape. This is not a model-dependent claim. It is a direct consequence of the cross-section for Lyman alpha absorption in neutral hydrogen, which is so enormous that even a modest column of neutral gas is sufficient to eliminate the signal completely. This is why, in the years before James Webb, the highest redshift at which a confirmed Lyman alpha emitter had been detected was around redshift 7.3, corresponding to a cosmic age of about 700 million years, by which time the universe had completed a significant portion of its reionization and the intergalactic medium had become substantially ionized. At earlier times, at higher redshifts, in a more neutral universe, no Lyman alpha emission should survive. It was considered a hard observational ceiling, a physical boundary. A rule, in early 2025, a paper published in Nature reported that this rule had been broken. The galaxy in question is designated JWST GSZ 13-1LA. It was discovered as part of the JWST survey in the JWST Origins field, the deepest region of JWST imaging, and identified as a photometric candidate at a redshift of approximately 13. A redshift of 13 corresponds to a cosmic age of roughly 330 million years after the Big Bang. This places it in the heart of the cosmic Dark Ages, at a time when the universe was, by every measurement and every model, predominantly neutral. The intergalactic medium at this epoch should have been between 80 and 99% neutral hydrogen, possibly more. Follow-up spectroscopy with NIRSpec, totaling 18.7 hours of continuous observation, confirmed the galaxy's redshift and then delivered the shock. In the spectrum, at the precise wavelength where Lyman alpha emission should appear, redshifted to an observed wavelength of 1.7084 micrometers due to the expansion of the universe, there was a line, a real, measured, statistically significant emission line detected at a signal-to-noise ratio of 6.4, consistently across two independent observing visits. Not a noise spike, not an artifact, a Lyman alpha line at a redshift of 13, in the middle of the Dark Ages, where Lyman alpha emission is not supposed to be visible. The team that reported the discovery, led by Joris Wittstock of the Cosmic Dawn Centre in Copenhagen, and the Cavendish Laboratory at Cambridge, and including many of the same researchers from the broader JWST collaboration, was careful to note that the signal is remarkable precisely because it cannot be explained by standard models. Lyman alpha emission has previously been confirmed in galaxies as early as redshift 7.2, and there have been detections at 7.5, one at 8.7, and one intriguing detection at 10.6 in the galaxy GNZ 11, which sits inside an unusually large ionized region. But the detection at redshift 13, at JWST GSZ 13-1LA, is more than 500 million years earlier than any previous confirmed Lyman alpha emitter. It is not a marginal extension of the known population. It is a categorical departure. The question the team had to answer was not whether the signal was real, but was established by the spectroscopy. The question was how it got out. How did Lyman alpha photons generated inside a galaxy 330 million years after the Big Bang manage to escape through an intergalactic medium that should have absorbed them? 3 mechanisms were considered. The first and most physically natural is that JWST 13-1LA had already carved out a bubble of ionized hydrogen around itself, a region of reionization local to that galaxy in which the surrounding neutral medium had been sufficiently ionized by the galaxy's own ultraviolet radiation to allow Lyman alpha photons to escape before encountering enough neutral gas to be absorbed. For this to work, the galaxy would need to be producing ionizing photons at an extraordinary rate. The team calculated the required ionizing photon production efficiency and found a lower limit of roughly 1026, 5 Hz per erg, a value so high that it exceeds what standard models of star-forming galaxies produce by a wide margin. It implies either that the galaxy contains stars of extreme temperature and luminosity, possibly including the hypothetical population 3 stars, the first generation of stars, formed from pristine hydrogen and helium, or that it contains an actively accreting supermassive black hole, generating the ionizing photons through a mechanism unrelated to stellar radiation. Second mechanism is geometric. Perhaps the galaxy's neutral gas is distributed inhomogeneously, in a patchy or disk-like configuration, such that Lyman alpha photons produced near the nucleus can escape along low Botanot's channels through the galaxy's own interstellar medium before reaching the intergalactic medium. This would require a specific, somewhat contrived geometry, but there is precedent for it in observations of compact star-forming galaxies at lower redshifts. The NIRSpec spectrum of JWST 13-1LA shows a smooth spectral turnover rather than a sharp Lyman break edge, which is consistent with the presence of dense neutral gas, a damped Lyman alpha absorber, within or near the galaxy itself. The third possibility, and the one that the team identifies as a viable alternative explanation, is that the emission is not coming from stars at all, but from an active galactic nucleus, a supermassive black hole accreting at a high rate, producing the ionizing radiation and the broad Lyman alpha line through its own physics. JWST 13-1LA is effectively unresolved even by Webb's sharp optics, with an inferred half-light radius of less than 35 parsecs. This extreme compactness is more consistent with an AGN than with a typical star-forming galaxy. AGN are known to have high ionizing photon escape fractions and can produce Lyman alpha emission through broad-line region physics. This is, to my mind, one of the most genuinely open situations in current observational cosmology. We have a real measured signal. We know it is there, we do not know what produced it or how it escaped, and each of the candidate explanations carries extraordinary implications if true. If JWST 13-1LA is ionizing its own surrounding medium, it is providing the first direct observational evidence that reionization began not from dense galaxy clusters but from individual, UV-faint sources embedded in the neutral IGM, a scenario with profound consequences for models of how reionization unfolded. If it contains population 3 stars, we have caught the first generation of stars in the act. If it contains a supermassive black hole, we are confronting the question of how a black hole of the required mass assembled itself in 330 million years of cosmic time, which is itself a separate and unresolved problem. Any of those answers is, as the paper title notes with characteristic scientific understatement, a witnessing of the onset of reionization. And then, before the community had fully digested JWST 14.0 and JWST 13.1LA, Webb's record-breaking streak continued. In May 2025, a new galaxy was confirmed with a spectroscopic redshift of 1444, designated MOM-Z14, the MOM standing for Mirage or Miracle, the naming conventions of the survey program that found it. This new object pushed the cosmic record back by another 10 million years. Light from MOM-Z14 left its source when the universe was approximately 280 million years old. It has been travelling toward us for 13.53 billion years, and like its predecessors, it is remarkably luminous, an absolute UV magnitude of roughly -20.2, bright enough to be detected in relatively shallow survey data, and is therefore raising the same questions about how the universe managed to produce such a luminous, presumably massive object so early in its history. The record for most distant confirmed galaxy has now been broken 4 times in 3 years. Webb owns the top positions on the list, and each new entry in that record book is not merely a statistic. It is a data point that presses harder on the same wound in our theoretical understanding. How did the universe get here this fast? I want to pause the science for a moment and tell you about a Thursday morning in January 2024. Because the history of astronomy is not just a history of instruments and equations. It is a history of people sitting in front of screens at improbable hours, waiting for data to resolve into meaning. And sometimes, rarely, but sometimes, the data resolves into something that makes even a trained scientist stand up and step away from their desk. Kevin Heinlein was not supposed to be working that morning. He is an associate research professor at the Steward Observatory at the University of Arizona, a person who has spent years building expertise in the photometric selection of distant galaxy candidates and who was deeply embedded in the JWST survey's effort to catalogue the universe's earliest objects. He had been involved in the identification and initial analysis of the source that would become JWST GZ14-0 since early 2023, when it first emerged from the JWST imaging data as an anomaly, too bright, too large, too far away by the prediction of every model the team had access to. The NIRSpec observation of the source had been scheduled for January 2024, nearly a year after the initial discovery. In those intervening months, the JWST team had done everything they could to test the photometric hypothesis, accumulating imaging in narrowband NRCam filters, modelling the spectral energy distribution, arguing internally about what the source was most likely to be. Some team members were cautious. A source that bright at that distance was unusual enough that imposter scenarios, a dusty galaxy at moderate redshift, masquerading as a high redshift object, remained on the table. The spectrum would settle it. On the morning after the observation, the data processing pipeline had reduced the raw NIRSpec data into a one-dimensional spectrum. Spectrum was shared with team members. Heinlein opened it, and when the spectral break appeared in the plot, the sharp, unambiguous discontinuity and flux at the wavelength corresponding to the Lyman alpha break at a redshift of 1432, he reportedly got up from his desk, not with excitement exactly, with something closer to the physical need to put space between himself and what he was seeing. That reaction, the standing up, the stepping back, is one of the things that tells you something genuinely unexpected has happened. Scientists are, by training and temperament, calibrated to be skeptical of their own results. The entire machinery of peer review, reproducibility, and statistical significance is designed to prevent us from being too easily excited by noise. When a scientist who has spent years studying distant galaxies gets up from their chair at the sight of a spectrum, it is because the signal is not noise. It is because the numbers are real. And the numbers are saying something that requires you to breathe differently for a moment. What Heinlein was looking at was a galaxy at redshift 14, 32, a number that at the time was more than one full unit of redshift beyond the previous record holder, itself a JWST galaxy at Z13.2 that had only recently been confirmed. The spectral break was unequivocal, there was no plausible contaminant. The Lyman alpha break was exactly where it needed to be for an object at that distance, and the rest of the spectrum, the blue continuum shortward of the break collapsing to zero, the red continuum rising consistently in the way models of star-forming galaxies predict, confirmed not merely the redshift but the nature of the source. It was a galaxy, sitting 290 million years after the Big Bang, glowing with the equivalent ultraviolet luminosity of hundreds of millions of solar masses of newly formed stars. Stefano Carniani, the lead spectroscopist on the JWST program, was based at the Scuola Normale Superiore in Pisa, Italy, 7 time zones ahead of Tucson. He had designed the IR-spec observing strategy for the JWST program and was deeply familiar with the technical uncertainties that attend high redshift spectroscopy. When the spectrum reached him, his response, later recorded in the official NASA announcement, was that seeing it was incredibly exciting for the whole team, given the mystery surrounding the source. That measured, Italian phrasing contains what I suspect was a great deal more than the words convey. The announcement of JWST GSZ 14-0's discovery, made in May 2024, was accompanied by a NASA blog post that is unusual in scientific communications for the degree to which it conveys the genuine surprise of the people involved. Heinlein and Carniani were invited to describe the finding in their own voices. Their account is worth reading in full because it captures something about the discovery moment that formal papers necessarily edit out. The mixture of vindication and bewilderment, the sense of being simultaneously right. The source is at high redshift, and confronted with a new problem, what does it mean that it exists? All of these observations together tell us that JWST GSZ 14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe they wrote. Those are precise words, not challenges our models, or is consistent with some scenarios, not like the types of galaxies predicted. The actual object is, in a direct and measurable sense, categorically different from what the simulations had produced. The MIRI observations, conducted as part of a separate guaranteed time program led by George Reek of the University of Arizona, added a further layer of astonishment. MIRI, the mid-infrared instrument, observes at wavelengths longer than NIRCam, and at the redshift of JWST GSZ 14-0, its bandpasses cover rest frame visible light, the light that the galaxy was emitting in the wavelengths our eyes can see, though massively redshifted by the time it reached Webb. Jake Helton, a JWST researcher also at Steward Observatory, analysed the MIRI data and found that the galaxy's brightness in those bands was higher than would be expected from a simple extrapolation of the near-infrared photometry. The excess implied the presence of strong emission lines in the rest frame visible spectrum, specifically hydrogen emission and critically oxygen emission. The forbidden transition at 88 micrometers in the rest frame, later confirmed by observations with ALMA, the Atacama Large Millimeter SOP millimeter array, would prove to be one of the most important measurements associated with this galaxy. It was Sander Schouws, a PhD candidate at Leiden Observatory in the Netherlands, who led the Dutch team that detected the oxygen in ALMA data and published the result in March 2025. In an interview with the European Southern Observatory, he offered a description that is among the most vivid I have encountered in recent science journalism. It is like finding an adolescent where you would only expect babies. The line is so precise that I find myself returning to it. It does not say the discovery is unexpected. It does not say it is unusual. It says that the classification of what you are looking at is wrong. Not a baby galaxy, an adolescent. Something that has already gone through stages of development that the laws of physics, as we understood them, said it should not yet have reached. I will admit, when I first read that sentence in the ESO press release, I sat with it for longer than I intended, because the image it contains is not just a metaphor, it is a measurement. To call JWST GSZ 14-0 an adolescent is to say, this galaxy has 10 times more heavy elements than expected for an object its age. It has already produced multiple generations of massive stars. It has already seeded its own interstellar medium with the carbon, oxygen and nitrogen that require entire stellar lifetimes to manufacture. In a universe that is 290 million years old, a universe that by all models should be hosting only the most pristine, primordial objects, this galaxy is chemically enriched beyond what anyone predicted. ALMA measurement also provided an extraordinary improvement in the precision of JWST GSZ 14-0's distance. The oxygen emission line, detected at millimeter wavelengths, allowed the team to calculate the galaxy's redshift to an uncertainty of just 0.005%, the equivalent of being accurate to within 5 centimeters over a distance of 1 kilometer. The revised, precise redshift is 14.18, placing the galaxy at a cosmic age of approximately 300 million years after the Big Bang, within the error bars of the original measurement, confirming its status as the most distant galaxy confirmed by spectroscopy at the time of publication, those 10 hours of near-spec time. That first morning when Kevin Hainline looked at a spectrum and felt compelled to stand, the months of ALMA observation time in the Atacama Desert to nail down an oxygen line at the edge of the visible universe. These are not abstract events. They are hours of human attention invested in the singular enterprise of understanding where everything came from, and they produced a result that, as of this writing, remains genuinely unexplained. Let me raise the stakes, because everything I have described so far, the record-breaking redshifts, the overabundance of heavy elements, the impossible Lyman alpha signal, is scientifically remarkable. But it is still, in a sense, confined to the question of what specific objects exist and when they formed. The truly civilization-scale implication of these discoveries is what they tell us about the process that made the universe inhabitable. And that process is reionization. We exist because the universe was reionized. This is not poetry. It is a statement about physical causation after the cosmic dark ages, after the long, lightless epoch of neutral hydrogen filling all of space. Something began to change. The first luminous objects, whatever they were, however they formed, began emitting ultraviolet photons with enough energy to strip electrons from hydrogen atoms. Each ionizing photon, once it escaped from its source, travelled outward into the surrounding intergalactic medium and created an ever-expanding sphere of ionized gas. These ionized bubbles grew, they merged, they percolated through the universe like bubbles in a foam, and over a period that lasted from perhaps 150 million years after the Big Bang to perhaps 1 billion years after the Big Bang, the hydrogen that had blanketed the cosmos was gradually stripped of its electrons. The universe became transparent again, not to visible light, as it had briefly become at recombination, but to the full spectrum of ultraviolet radiation. The darkness ended. This matters for human existence, because the opacity of neutral hydrogen is indiscriminate. In a universe that has not been reionized, ultraviolet light cannot propagate. And ultraviolet light, despite its reputation for causing sunburn, is also the driver of the photochemistry that strips out the molecular hydrogen in star-forming clouds, regulates the temperature of the interstellar medium, and influences the formation of complex molecules, including the building blocks of biological chemistry. A universe that had never been reionized would be, at minimum, a universe whose chemistry evolved very differently from the one we inhabit. The current consensus is that the intergalactic medium remaining in a neutral state indefinitely would have severely suppressed later galaxy formation, as neutral hydrogen cannot cool and collapse efficiently in the presence of a dense ionizing background. In the darkest version of this counterfactual, you do not get spiral galaxies, you do not get planetary systems, you do not get us. So when we ask which objects reionized the universe, we are asking about the agents of our own cosmic biography. The standard answer before JWST was probably a large population of faint, low-mass galaxies collectively producing enough ionizing photons over a long enough timescale to complete the job by redshift 6. This was consistent with what Hubble could observe, a large number of faint galaxies at redshifts of 7, 8, and 9 that together could, with plausible assumptions about photon escape fractions, account for the ionizing budget. Bright galaxies and quasars were thought to be insufficient in number at early epochs to drive reionization on their own, though they certainly contributed. JWST is complicating this picture in 2 directions simultaneously. First, the sheer number and brightness of galaxies at redshifts above 10. The population that the bright galaxy problem draws attention to suggests that the early universe was producing luminous structures far more efficiently than models suggested. If there are many more bright UV-luminous galaxies at early times than we predicted, then the ionizing photon budget may have been dominated by a smaller number of more luminous sources rather than a vast army of faint ones. This would change the morphology of reionization, the geometry of how the ionized bubbles grew and where they grew first, in ways that are directly testable with next-generation radio telescopes sensitive to the 21 centimeter emission of neutral hydrogen. Second, the discovery of JWST 13-1 the galaxy that appears to be broadcasting Lyman alpha emission from inside the dark ages, provides the first observational anchor for when reionization began, not merely when it ended. The presence of an ionized bubble around that galaxy at a cosmic age of 330 million years, inferred from the transmission of its Lyman alpha signal, suggests that reionization was already locally underway at that epoch, which means the process must have started earlier than 330 million years after the Big Bang, possibly much earlier, possibly within the first 100 or 200 million years of cosmic history. If reionization began that early, the objects driving it at the very beginning were not the luminous galaxies that Webb has been finding at redshifts of 14 and beyond. Those galaxies are likely too rare, too massive, to have done the job on their own at such early times. The earliest ionizers may have been population 3 stars, the hypothetical first stellar generation, formed from pristine hydrogen and helium, predicted to be extraordinarily massive and luminous and capable of producing ionizing photons at efficiencies far exceeding anything observed in the modern universe. Population 3 stars are one of the most important unconfirmed predictions in all of astrophysics. Every model of early star formation predicts they must have existed. The chemical enrichment of the universe, the presence of any heavy elements anywhere, requires them, because without a first generation of metal-free stars to manufacture and distribute those elements, no subsequent generations of stars could form with any metallicity at all. And yet, in the decades of searching before JWST, not a single population 3 star or population 3 stellar system had been directly detected. They are, by definition, the most distant objects we can conceive of observing. They formed in the smallest, earliest, least massive systems in an epoch that no previous telescope could reach. They are the original darkness breakers, and we have never seen them, or had not until recently. In April 2026, a paper announced what its authors described as the strongest evidence yet for the detection of population 3 stars in the distant universe. The detection was associated with a gravitationally lensed system, LAP-1b, in which JWST observations revealed a spectrum with chemical properties consistent with a stellar population of essentially zero metallicity, the chemical fingerprint of a first-generation stellar system. Previous tentative identifications had been made but failed to survive scrutiny. This new result was more robustly established, though the authors, with appropriate scientific caution, continued to use the language of candidate and strong evidence rather than confirmed detection. If that detection holds, and the coming years of Webb observations will be devoted, in part, to building on it, then we will have directly observed for the first time the objects that turned the universe's lights on, the first stars, the original light sources at the end of the cosmic dark ages, objects that existed perhaps 100 to 200 million years after the Big Bang, and that left their imprint on everything that came after them, including, ultimately, every atom of carbon in every living thing that has ever existed on this planet. I find it genuinely difficult to convey the scale of what that would mean. We are talking about the detection of objects so ancient, so foundational, that their existence is a prerequisite for the existence of the detector that found them. JWST is built from metal alloys, optical coatings, electronic circuits, and insulating materials. Every gram of those materials beyond hydrogen and helium was forged inside a star, most likely multiple generations of stars. The telescope that found the first stars is made, in part, of the ashes of earlier stars. It is the universe's own instruments being used to observe the universe's own origin. The recursion is not a metaphor. It is a fact of nuclear physics. the population 3 question is only one of 3 enormous unknowns that these recent discoveries have opened. The second is the question of what JWST GSZ14-0 actually represents, not as an individual object, but as a data point in the distribution. And the third, which carries perhaps the greatest long-term significance, is whether the theoretical framework, lambda CDM, can be made consistent with what JWST has found, or whether what JWST has found requires something new. Let me be careful here. This is the section of the script where the distinction between what the evidence shows and what the evidence implies matters most, where the temptation to overstate in either direction is most acute. The temptation to conclude that lambda CDM is broken is understandable given the volume of headline-generating surprises that JWST has produced. The temptation to dismiss all tension as consistent with known uncertainties is equally understandable given the enormous investment that the theoretical community has in a framework that has, after all, successfully predicted an extraordinary range of cosmological observations. The honest assessment, as of mid-2026, is this: lambda CDM is under more observational pressure than it has been at any point since the discovery of cosmic acceleration in the late 1990s. That pressure is not yet sufficient to require abandoning the framework, but it is sufficient to require taking seriously the possibility that the framework is incomplete in ways that the JWST data is beginning to reveal. To understand where the pressure lies, it helps to understand what lambda CDM actually predicts about the earliest galaxies. The model, coupled with the current best understanding of galaxy formation physics, predicts a luminosity function, the number density of galaxies as a function of UV luminosity, that evolves smoothly with redshift. As you go to higher redshift, both the number density and the luminosity of the brightest galaxies should decline. The reason is simple: there has been less time to assemble mass, and the gravitational structures that host galaxies, dark matter halos, have had less time to grow. The UV luminosity function at redshifts above 10, now measured for the first time by JWST with genuine spectroscopic confirmation, does not look exactly like what the models predicted. The bright end, the tail of the most luminous galaxies, is populated by more objects than expected. Not slightly more, systematically more, across multiple independent surveys, multiple teams, and multiple analysis methods. This excess at the bright end is now established observationally with a robustness that makes it difficult to dismiss as a systematic error in a single analysis. Several explanations have been proposed, and I want to work through them carefully, because this is where the science is genuinely live. The first and most conservative explanation is that early galaxies convert gas into stars with greater efficiency than the models assume. Lambda CDM's predictions for galaxy luminosity are not direct outputs of the dark matter physics. They are coupled to a layer of baryonic physics that is far less certain. Star formation efficiency, the fraction of available gas that actually gets turned into stars, is poorly constrained at high redshift. If early galaxies are simply better at forming stars, perhaps because they haven't yet developed the feedback mechanisms that suppress star formation in more evolved systems, then their luminosities can be higher without requiring any new physics. This explanation is popular because it requires the fewest modifications to the framework. Its weakness is that it tends to require very high efficiencies, in some cases approaching 100% conversion of available gas into stars, that seem physically difficult to sustain, and that are inconsistent with observations of equivalent star-forming systems at lower redshift. The second explanation involves the stellar initial mass function, the distribution of stellar masses produced when a cloud of gas fragments and forms a population of stars. If early galaxies preferentially form more massive stars, a top-heavy IMF, those stars are intrinsically more luminous per unit of stellar mass, so the galaxy appears brighter without actually being more massive. This explanation is compelling, because there are theoretical reasons to expect the IMF in metal-poor environments to be skewed toward high masses. Pristine gas lacks the cooling channels that metal-enriched gas has. which means it must fragment into larger clumps before collapsing. If the first-generation stars in these early galaxies were preferentially massive, that would simultaneously explain the excess luminosity and the presence of heavy elements like oxygen in galaxies as young as JWST 14-0. More massive stars produce more heavy elements more quickly and die sooner. The third explanation, and the one that has been gaining traction as JWST's AGN detection capabilities have revealed an unexpected abundance of accreting black holes at high redshift, is contamination of the luminosity function by active galactic nuclei. When an AGN is present, its accretion luminosity can significantly boost the apparent UV output of the host galaxy, making it appear more massive than it actually is. Several of the universe breaker candidates identified in 2022 and 2023 have subsequently been revealed, upon spectroscopic follow-up, to harbour AGN. Though not all of them, and the AGN contribution does not fully explain the excess. The fourth explanation, which is the most theoretically radical, is that lambda CDM itself needs modification, that either the dark matter physics or the dark energy physics, or the initial conditions set by inflation, are different enough from what we have assumed that the early assembly of structure proceeded faster than the standard model allows. This category of explanation includes exotic dark matter models in which the dark matter is warmer or more self-interacting than standard cold dark matter, modified gravity theories, and cosmological models in which the primordial power spectrum, the distribution of density fluctuations imprinted by inflation, has more power on small scales than the simplest inflationary models predict. Each of these explanations is being actively explored by the theoretical community. The challenge is that JWST has not yet provided a single dataset that uniquely discriminates between them. The bright galaxy problem is a statistical measurement. It tells us that the overall distribution of galaxy luminosities is inconsistent with the best current models. But it does not tell us which assumption in those models is wrong. That requires more detailed measurements, precise stellar masses from spectroscopy, star formation histories from multi-wavelength photometry, measurements of chemical abundances in individual systems, and ultimately a census of the galaxy population at redshifts above 14 that is large enough to be statistically robust. That census is being built, observation by observation. MOMZ14 at redshift 14.44, confirmed in May 2025, is part of it. The photometric candidates in the cosmos field that the MOM program is systematically following up are part of it. A galaxy detected in JWST MIRI imaging at 7.7 micrometers, identified as a candidate beyond redshift 14 on the basis of photometry alone. The detection reported by Jake Helton and colleagues is part of it. Each new confirmed object at extreme redshift adds a data point to the distribution that theorists must match. And here is the thing that I find genuinely unsettling about this accumulating body of evidence. The objects keep being there. Every time a new record is set, the record holder turns out to be bright, unexpectedly, anomalously bright. Jade's GSZ14 is bright. HOMZ14 is bright. Its absolute UV magnitude of -20. 2 makes it comparable in luminosity to galaxies at much later cosmic epochs. If the bright galaxy problem were a statistical fluctuation, a sampling artifact from observing a small patch of sky and happening to catch an unusually overdense region, you would expect the record setters to become fainter and more typical as the sample grew. Instead, each new record holder is luminous. Each one presses the same wound. Each one says the same thing to the models. You predicted something fainter than this. There is also a separate and specifically troubling issue raised by the oxygen detection in Jade's GSZ 14-0, the presence of an 088 micrometer emission line, the far infrared cooling line of doubly ionized oxygen at a redshift of 14.18, detected with ALMA, is among the most diagnostically powerful measurements that has been made of any object in the early universe. The oxygen abundance inferred from this detection is approximately 10 times the value that models of galaxy evolution at this epoch would predict for an object of Jade's GSZ 14-0's inferred mass and age, 10 times. not 2 times, which might be explained by model uncertainties, not 3 or 4 times, which might be explained by assuming an unusually efficient star formation history, 10 times the expected oxygen abundance in an object whose age is constrained by its redshift to a few 100 million years at most. This requires either that the enrichment proceeded at a rate that no standard model of stellar evolution and galaxy chemistry can currently reproduce, or that we are fundamentally misunderstanding some aspect of the chemical enrichment of early galaxies, perhaps the stellar initial mass function, perhaps the timescale of stellar evolution in metal-poor environments, perhaps the fraction of stellar ejecta that is retained in the galaxy rather than expelled by feedback. What Stefano Carniani said when confronted with the ALMA result: "I was astonished by the unexpected results because they opened a new view on the first phases of galaxy evolution," is the precise reaction of a specialist confronting data that does not fit any of the scenarios he had been trained to consider. That astonishment is not naive wonder. It is the specific, calibrated response of someone who knows how tight the model predictions are, and who is seeing the data exceed them by a factor that cannot be hand-waved away. There are also questions about reionization morphology that these discoveries force upon us. If galaxies like JWST 14.0 and JWST 13.1LA are more common than models suggest, if the bright end luminosity function is as elevated as the JWST data implies, then the process of reionization may have been dominated by objects very different from the faint, low luminosity population that most models identified as the primary agents. A reionization driven significantly by bright, massive galaxies and AGN would have proceeded through a different geometry, larger ionized bubbles, more rapidly growing, nucleated around the most luminous sources, rather than diffusely percolating through a uniform distribution of faint emitters. This is detectable. The 21 centimeter line of neutral hydrogen, observed in emission by neutral gas before and during reionization, and in absorption by neutral gas against the cosmic microwave background, is the primary observational probe of the large-scale morphology and timing of reionization. Experiments like the Square Kilometre Array, currently under construction in South Africa and Australia, are designed specifically to map the 21 centimeter emission as a function of redshift and position on the sky, producing a three-dimensional picture of when and where the first ionized bubbles appeared, how large they were, and how they grew. If JWST is right, if reionization was driven by a more luminous, rarer population of sources than models predicted, then the SKA should see a particular pattern: fewer, larger, more isolated bubbles rather than many small bubbles distributed uniformly across the sky. The cross-validation between JWST's discoveries and SKA's forthcoming maps is one of the most anticipated scientific experiments of the next decade. It is the test that will tell us whether the universe's story of first light matches between the two most powerful instruments ever built to study it. But there is one more open question that the JWST data has introduced, one that I would argue has the potential to be the most consequential discovery in this field since the measurement of the Hubble constant, and it concerns not the brightness or the chemistry or the reionization morphology of these early galaxies. It concerns their very existence in a context that the standard model does not currently have a fully satisfying explanation for. The structure formation timeline in lambda CDM begins with quantum fluctuations in the inflationary epoch, fluctuations in the energy density of the primordial universe that, as the universe cooled and matter dominated, became the seeds of gravitational collapse. Those seeds grew hierarchically. Dark matter first collapsed into the smallest halos, which merged into larger ones, which eventually accumulated enough gas to form the first stars. The time available from the Big Bang to the formation of JWST 14.0 at cosmic age 290-300 million years is not very much by galactic standards, but it appears to have been enough to produce a galaxy of several 100 million solar masses in stars, with significant chemical enrichment and dust. Whether this is achievable within lambda CDM depends on the specific parameters of that framework. the amplitude of the primordial power spectrum, the properties of dark matter, the efficiency of early star formation. The most recent analyses, notably the work published in Astronomy and Astrophysics by Carniani and colleagues following the ALMA oxygen detection, suggest that while JWST 14 GROW is challenging for standard models, it is not yet definitively outside the parameter space they allow. It is an extreme case, not an impossible one, but extreme is doing a lot of work in that sentence. The tail of a probability distribution can be rare and still be within the distribution. The question is, what happens when you find not one extreme object, not 5, but dozens, when the tail of the distribution appears systematically too populated to be consistent with the underlying distribution you assumed? That is, the regime JWST is approaching, and it is the regime in which, consistent with large uncertainties, becomes harder and harder to maintain. I should acknowledge one more dimension of this problem that is not always made explicit in popular coverage. The tension between JWST observations and lambda CDM predictions is not the same as saying that lambda CDM is wrong. It might be saying that our galaxy formation models, the baryonic physics layered on top of the dark matter structure, are wrong. It might be saying that our understanding of stellar physics in metal-poor environments is wrong. It might be saying that the contribution of AGN to high redshift galaxy luminosities is systematically underestimated. These would all be serious revisions, but they would not require modifying the foundational cosmology. What would require that modification is a discovery, perhaps coming in the next few years of JWST operations, of an object so massive, so luminous, and so definitively stellar in origin that no combination of baryonic physics adjustments can account for it. That discovery has not yet been made, but the trajectory of the observations over the last 3 years suggests it is not implausible, which raises a question about the next few years of observation and about what comes after JWST, because the story being told by these discoveries is not finished. It is, if anything, accelerating. The James Webb Space Telescope was designed with a mission lifetime of 10 years. It launched on December 25, 2021, and its propellant, needed to maintain its orbital position at the L2 Lagrange point, is expected to last somewhere between 20 and 30 years, far exceeding the original mission specification. That means that the discoveries described in this script are not endpoints, they are openings. The JDIS program is ongoing. The spectroscopic follow-up of photometric candidates at the highest redshifts will continue year by year, pushing the confirmed population of extremely early galaxies to larger numbers and better statistics. The MOM program, the Cosmos Field Survey that produced MOM Z14, will continue cataloguing candidates and triggering spectroscopic confirmation of the most promising ones. The near-term scientific agenda in this field is focused on 3 priorities. First, characterizing the population of galaxies at redshifts above 12, with sufficient statistical rigor to produce a robust UV luminosity function that theorists can actually test against models. Not just a handful of confirmed record holders, but a sample of dozens or hundreds of spectroscopically confirmed objects spread across multiple fields and covering a range of luminosities. Second, measuring the chemical properties, the abundance of oxygen, carbon, nitrogen, and other elements in as many of these early systems as possible, using both JWST's spectroscopic capabilities and ALMA's millimeter wave sensitivity to constrain the star formation histories and stellar physics of the earliest galaxies. Third, building the census needed to determine whether population 3 stars, the first-generation metal-free stellar systems, are detectable at the sensitivities Webb can achieve. The population 3 question is particularly urgent, and the answer will likely come from gravitational lensing. When JWST looks at galaxy clusters that act as natural gravitational lenses, magnifying the light of background objects by factors of 10, 20, or even 50, it can reach effective sensitivities far beyond what it could achieve in blank fields. The LAP1b detection that produced the strongest population 3 evidence as of April 2026 exploited exactly this magnification. future programs targeting carefully selected lensing clusters, chosen to maximize the probability of intercepting a line of sight to a very high redshift, metal-free source, represent the best current strategy for directly detecting the universe's first stars. Beyond JWST, the observational landscape over the next decade includes the extremely large telescope, the 39-meter ground-based optical and infrared telescope under construction at Cerro Amazones in Chile's Atacama Desert, expected to see first light in the late 2020s or early 2030s. The ELT's primary mirror collects more than 36 times the area of a single 6.5-meter aperture, even accounting for the advantages that JWST enjoys from observing above the atmosphere. The ELT's raw collecting power will allow it to perform spectroscopy on faint sources that JWST identifies but cannot characterize in detail. The combination of JWST for discovery and photometric screening, ALMA for millimeter wave chemical characterization, and the ELT for deep optical infrared spectroscopy represents a synergy of instruments that, over the next decade, will produce a genuinely comprehensive picture of the first billion years of cosmic history. Complementing this optical and infrared program is the Square Kilometre Array's 21-centimetre experiment. The SKA Lau array, currently being constructed in the radio-quiet zones of Western Australia, will attempt to detect the redshifted 21-centimetre emission of neutral hydrogen across the epoch of reionization, mapping the morphology and timing of the process in 3 dimensions. This measurement is extraordinary in its ambition and extraordinarily technically demanding. The 21-centimetre signal from the epoch of reionization is fainter, by orders of magnitude, than the foreground emission from our own galaxy and other radio sources, and extracting it requires calibration and foreground removal techniques of extraordinary precision. But if the SKA Lau succeeds, and significant resources are being invested in demonstrating that it can, it will provide a global picture of how and when reionization unfolded across the entire sky. That picture, cross-correlated with the galaxies that JWST has confirmed as existing during their epoch, will identify which of those galaxies are sitting inside ionized bubbles, and in doing so identify the actual agents of reionization. This is, I think, one of the most underappreciated aspects of what is currently unfolding in observational cosmology. We are in the opening phase of a period in which we will move from knowing that reionization happened, which was established in the early 2000s, to understanding, in quantitative detail, how it happened, who did it, and how quickly. That transition from knowing a fact to understanding a process is, historically, where cosmology has undergone its deepest revisions. We knew the universe was expanding before we understood dark energy. We knew the universe had a hot, dense beginning before we understood the detailed physics of Big Bang nucleosynthesis. We knew there was dark matter before we understood, or rather, before we failed to understand, since we still don't, what it is. The question of reionization is at the same stage. We know it happened. We know roughly when it ended. We now, thanks to JWST GSZ 131LA, have the first direct evidence of when it was beginning. What we do not yet know is the full accounting. Every source that contributed ionizing photons, their luminosity distribution, their clustering, their escape fractions, their masses. We do not know whether population 3 stars played a significant role, or whether they were overwhelmed by the more luminous but less pristine galaxies that JWST has found at redshifts of 13 and 14. We do not know whether the AGN that JWST is revealing at surprisingly high abundances in the early universe are sufficiently numerous and luminous to have contributed significantly to the ionizing budget. We do not know whether the morphology of reionization was inside out, with the densest regions being ionized first by their concentration of luminous sources, or outside in, with the voids being cleared first by the photons leaking from their edges. Every one of those unknowns is now being actively addressed by ongoing observations, and the answers, when they come, will arrive faster than at any previous time in the history of cosmology, because the instruments available to the field have never been more powerful, more complementary, or more purposefully designed for this specific set of questions. There is one discovery that, if made in the next 5 to 10 years, would, in my assessment, be more consequential than any of the ones described in this script. It would be the spectroscopic confirmation of a galaxy, or a stellar system within a lensed arc, at a redshift above 20. A redshift of 20 corresponds to a cosmic age of approximately 180 million years after the Big Bang. This is a time at which, according to virtually every model of structure formation, the universe contained no objects more massive than perhaps 1 million solar masses, protostellar clusters at most, embedded in the very first dark matter halos. A confirmed galaxy at redshift 20 would not merely challenge lambda CDM, it would require new physics. It would, as several theorists have noted privately, be a crisis in the strict scientific sense of the word. Photometric candidates at redshifts approaching 20 have already appeared in JWST data. None has yet been confirmed spectroscopically, and several have been shown upon follow-up to be at lower redshifts than first suspected. But the fact that candidates exist at all is not trivial. The telescope is finding things to point at. The observations are in progress. The answers are coming. In the meantime, the three great open questions: how did the first galaxies form so fast? What broke the silence of the Dark Ages? Are the first stars now within reach of detection? Continue to run simultaneously, unresolved, pulling the field forward. That is not a failure of the science. It is the science working as it is supposed to work. Each answer opening three more questions, each new instrument revealing not the expected simplicity, but the actual complexity of the universe that is already out there, waiting to be described. There is something that I have been sitting with since I first began researching this script. It is not a scientific question, or not only a scientific question. It is something older than that. For most of human history, the word before had a finite limit. You could ask what came before the pharaohs, before the first city, before language, before the first human. You could always push the question back further. But at some point, you reached a wall. The past became inaccessible, not because it didn't exist, but because no record of it survived. The universe before a certain depth was silent. We are living in the first generation of humans who can push before back to 280 million years after the beginning of everything. We can look at JWST GSZ 14-0, a faint smear of light in a patch of sky the size of a grain of rice held at arm's length, and know that the photons forming that image left their source before the Earth existed, before the Sun existed, before most of the stars in the Milky Way existed. We can know from the wavelength of an oxygen emission line measured by a radio telescope array in the Chilean Atacama Desert that a galaxy 13, 4 billion light-years away, had already cycled through multiple generations of stars, had already lived several stellar lifetimes, in the time it took the Milky Way to form its first globular clusters. This is not impressive the way a tall building is impressive, by simple accumulation of scale. It is impressive in the way that certain mathematical proofs are impressive, by the unexpectedness of the route from premise to conclusion. From a telescope orbit 1.5 million kilometers from Earth, from a spectrograph with shutters smaller than a human hair, from 10 hours of photon counting in the near-infrared, to a number, 14.32, that places a galaxy 290 million years into the life of an infinite universe. The compression of cosmic time into a single redshift measurement is one of the genuinely vertiginous achievements of modern science. And yet the discoveries described in this script are, each one of them, not endings but openings. JWST GSZ 14-0 is the most distant confirmed galaxy, for now. MOM-Z14 briefly took the record in 2025 and will itself be surpassed by something. Webb is probably already imaging in its current observing programs. JWST GSZ 13-1LA has produced the first Lyman alpha signal from the Dark Ages, but it is one object, and the field needs a population. The population 3 stellar candidates are compelling, but not yet definitive. The confirmation of the first stars requires more, and harder, spectroscopy than any single program has yet delivered. What connects all of these discoveries, the overabundant bright galaxies, the impossible Lyman alpha signal, the oxygen in a 300-million-year-old galaxy, the chemistry of adolescent structures where the universe had promised only infants, is that they all point in the same direction. They say, in different ways and with different evidence, that the universe's early life was more vigorous, more rapid, and more chemically productive than the standard model of the slow hierarchical build-up of structure had led us to expect. The universe, it turns out, was not a patient infant growing gradually toward complexity. It was already running, building, enriching itself at an age when we had barely expected it to be walking. That is, to my mind, one of the most consequential shifts in cosmological intuition that has occurred in my lifetime. Not because it definitively breaks any particular model. The theoretical community is resilient and creative, and will find ways to accommodate the data within frameworks that preserve much of what we know. But because it means the universe has a character that we had misread. It is a more energetic, more self-organizing, more chemically ambitious thing at its earliest moments than the equations had suggested. There is a version of this story that could be told as loss, as the story of theories under threat, of decades of work challenged by a single telescope. But I don't read it that way. I read it as the universe being more extraordinary than we had modelled, which is, historically, the direction that cosmological surprises tend to run. The universe is not usually simpler than expected. It is usually, when we look more carefully, more complicated, more structured, or layered with physical processes we had not fully appreciated. The cosmic dark ages are not, it turns out, entirely dark. The first light arrived earlier than we thought. The first elements formed faster than we thought. The first ionizing sources punched through the neutral fog before our models said they should have. We are the first generation of humans to know this. We are the first generation to have seen directly a galaxy that formed when the universe was less than 1% of its current age. We are the first generation to have detected the chemical fingerprint of oxygen in a galaxy that was old when the Earth's sun was not yet dust. We are the first generation in which the phrase, the edge of the observable universe, has ceased to be entirely figurative and has become, in certain wavelengths with certain instruments, an actual destination, a place we have looked at, measured and described. The cosmic dark ages ended hundreds of millions of years ago because something in that lightless void finally accumulated enough matter to ignite. The darkness broke, light spread, and eventually, billions of years later, in a universe that had used that light and its chemistry to build planets and atmospheres and nervous systems, a species evolved that was curious enough to build a golden mirror and send it to the cold dark between the planets to look back at that first moment, to find the first object to break the silence, to hear, across 13 billion years of cosmic expansion, the first whisper of light in a universe that had been dark for longer than we knew how to imagine. We heard it. The question now, the question that will occupy the generation of cosmologists currently in their graduate programs, the question that the extremely large telescope and the square-kilometre array will spend decades addressing, is not what it sounds like. It is where it came from. And that question, unlike the question of what the universe contains, does not yet have an answer. It has a horizon. And perhaps that is the more honest place to leave it, not at the destination, but at the next edge of the known, where the light is already gathered in the mirror, and the spectrum is already processing, and somewhere in a fluorescently lit office in Tucson or Pisa or Copenhagen, someone is about to look at a screen, sit very still for a moment, and then stand up. That moment, the standing up, is where the history of the universe is still being written, and we are living in it.